And welcome to the video lecture accompanying chapter 17 on the topic of analyzing starlight. So this is our lecture for week 4 of the class, and we've jumped from chapter 3 to chapter 17 because chapters 4 through 16 cover the solar system, which is covered in a different class. So we're moving on past the solar system. So all our topics now are going to be things in distant space, stars, galaxies, and even the beginning of the universe itself. Okay? So let's talk really about a chapter that represents the fundamentals of looking at stars, okay? Because if we're going to spend some weeks talking about stars and their life cycles and everything that they do, then we need to understand how they're observed. And in the same way maybe we talked about the history of astronomy and how we got to the point of understanding modern astronomy, we're going to focus on the methods, the history of analyzing starlight. So let's think of what's going on here. So notice in this long time exposure, we see the colors of the stars. They're not all the same color. Some are red, some are blue, some are orange, and they're all represented here as the streaks in this long exposure photograph. Let's look at another one, right? I'll go back to the previous slide. Here, again, we're looking at all these different colored stars. As it says, shining like jewels. We see red ones, orange ones, right? Kind of whitish ones. Our star kind of falls into the white category, all right, because it's got just as much red as blue, so the colors kind of balance out and it's more white. Some are more orange though, all right? Our star looks orange through our atmosphere, okay? But through space it would not, all right? So why is that? Why are stars different colors? It's a fundamental question, right? It's a question like a 5-year-old would ask. It's a great question because in answering it, we're going to get into understanding stellar temperature, all right, and a lot of key properties, ultimately the chemical properties, the physical properties of stars, because stars of a certain color are stars of a certain temperature, are stars that undergo certain processes, certain physical processes inside of them. Okay, let's take a step back and just think about looking at stars. So you look up into the sky and you see some stars are brighter than others. Okay, that would have been in the last two photographs, just the bigger ones in the Hubble telescope photograph, or the ones that made thicker streaks across the sky. But to the naked eye, it's clear. Some are just easier to see. Some you can't see if there's light pollution, like from a street light or in the city, right? So what does that mean? How do we think about the idea that some stars are brighter than others? Well, we need to quantify it because we're in science, right? And we quantify it with the idea of apparent magnitude. Sometimes it's called apparent brightness. Those are interchangeable terms. All right? So apparent magnitude is a scale. So right now, just think of it as a number. Let's look at that scale. Excuse me. So we can see the very, very brightest thing in our sky, because apparent magnitude is apparent. It's us as observers on Earth, okay, is the sun. The brightest thing out there. So the sun has the largest apparent magnitude of anything, and that is -27. Hold up. Wait, -27 is the biggest? But wait, over here there's bigger numbers, like 30 and 25 and 20. That's because this scale is such that the larger negative number is the brighter. Okay? So brighter things are in this direction. Okay? You're probably thinking that's a terrible idea. Why not just call the sun 100 and then, have everything? Because this scale is not linear, it's a logarithmic. I'll talk about that, I'll show how we solve it. And the reason it is, and if you haven't seen logarithmic scales, it's a lot to take in at first, but the reason is because the brightnesses vary so much. So we're talking about brightnesses that are hundreds of thousands of times brighter. So the sun is hundreds of thousands, even millions of times brighter than the faintest stars that we can see with the naked eye. But of course it is, right? Because you can look at those stars and when it talks about eye damage from them, the sun, you just stare at it for a minute or two and you've permanently damaged your eyes. So that's a huge difference. That's got to be. And because the difference is so large, we have to use special math, the math of logarithms, to talk about it. And because of that, the negative naturally comes out because logarithms have to do with exponents, and exponents can have negative values if the exponent is in the denominator. You might remember that from a math class. So that's where the negative comes from. But the thing you got to remember is brighter objects are more negative. And there's actually not many objects in the sky that even have negative values of apparent magnitude, right? There's the sun, the moon, right? Here's the moon at like -13. right? And then there's a couple more, right? So the planets, definitely. Now the planets vary in brightness depending on where they are in the orbit around the sun relative to where we are in our orbit around the sun. But when Venus is closest to us, it can be really bright. For that matter, even actually brighter, potentially brighter than Venus, is going to be Mars sometimes. Let's see. Oh yeah, Mars, okay. But not always. Venus really can be the brightest. Oh man, sometimes in the morning sky, because Venus you can really only see, and I mentioned this before, immediately after sunset and immediately before sunrise, because it's interior of our orbit, right? So think, if you just think 3D, you know, in order to get that view of Venus and not have the view of Venus washed out by the sun, then there's not many opportunities to do that, right? Because if Venus is between us and the sun, we're not seeing it at night, are we? Right? Anyway, so Venus is so incredibly bright sometimes. It doesn't seem like it's a planet. It seems like it's an airplane, you know, but it's just not moving. It's kind of unreal. All right. So then we got Jupiter, Mars, and so on, like I was saying. And then really look, Sirius, okay? And that's basically it. There are no other stars in the sky that actually are so bright that they would have a negative value of apparent brightness. We get to like Alpha Centauri and Betelgeuse and Polaris. Those are really bright stars, and they have values like Polaris of 2, right? But that's it, you know? So it really is a testament to the fact that Sirius is such a bright star. It's a good one to know, okay? And then we get on to the faintest object visible to the unaided eye at about a 7, all right? And then with binoculars, you can get up to an apparent brightness of about 10. Telescopes, right, over here. And then finally we get up to like Hubble, the very, very best telescopes in the world, and we can see these things that are so incredibly faint, right? 30 is very, very faint. You need a good telescope, preferably outside of the Earth's atmosphere to see it, okay? All right? So that's the scale. But what does the actual calculation look like? Right, so I want to show you the calculation. I'm going to do one example. There's another couple examples in your book. So the formula is this. It's B2 over B1 equals 2.5. That's just a coefficient that's chosen for this particular scale to get it to fit the way astronomers want to. There's no like special meaning to it. But then look at the exponent. M1 minus M2. So the reason there's a 1 and a 2 in both this letter B and letter M, which I'll explain what they are. But the reason there's 1 and a 2 in the first place is because whenever we talk about apparent magnitudes, we have to compare to something else. The scale is only meaningful if we're comparing between two objects. Okay? So then let's compare between Polaris and I just want to make it interesting. How about Polaris and Venus, right? I made a big deal about how bright Venus can be and how if you're really lucky to see it in the early morning or right after sunset. So let's do it. Let's compare Polaris, a star that we know is the North Star, right? That we probably, maybe looked up at it, to how bright Venus can be, all right? So what I'm going to do is I'm going to compare their apparent magnitudes, okay? And we're going to use 2 and negative 4 as the rough estimates from this figure here. And then I'm going to solve for the ratio of B2 to B1, all right? So then what I'm saying then is that M1 and M2 are the apparent magnitudes, right? So M for magnitude. And I obviously interchangeably call that apparent brightness, okay? So we want Venus to be M2. And the reason for that is because we want to find this ratio here with Venus on the top, because that will tell us how much brighter Venus is, all right? And then we're going to define Polaris as M1. So M2 for Venus, M1 for Polaris, specifically Venus at its brightest, right? Okay, and then 2.5 is obviously just numbers. Now I'm finally going to tell you what is B2 over B1. So B2 over B1 is ratio of true brightness. Because apparent brightness is how far these stars, basically how bright they appear to us, right? But then we want to find the actual change in luminosity, right? How bright is Venus truly compared to, to Polaris, okay? And let me be careful here. I guess I want to define, and let's see if I'm gonna remind myself if I'm gonna speak about this again. Yeah, so I'm about to spend a minute, because okay, when I'm talking about true brightness, I'm still talking about something that's relative to Earth. Because of course, we don't know how bright Polaris would be if we got it close to it. What if we just took our planet and threw it into orbit around Polaris? Because it's a star after all. And if we did that, then of course it'd be incredibly bright. It'd be brighter than the sun relative to us because it's a bigger star, okay? So that means that true brightness isn't an actual feature of the object itself. It's still just how it appears to us. But the reason that I'm going to call it true brightness, or at least a true brightness ratio, is because it does have to do with the actual amount of energy that's reaching us, okay? And it's not just a coefficient. It's not just a scale. So you can really think of this example as just making sense of the figure above, of figure 17.2, okay? Just understanding what a logarithmic scale means, okay? And hold that thought, because then I'm going to explain what luminosity is. And then I will call that true luminosity. So that means we're going to distinguish between apparent magnitude, brightness, and luminosity, okay? All right, but I'll summarize that after we do this, okay? So what we're going to go ahead and do then is find that ratio. So B2 over B1, and then 2.5, and we were to the power of, so we had 2, and then minus -4. Okay, so 2 minus -4 is the 6th. So then what we're doing is we're raising 2.5 to the 6th power. Okay, so you can do this on a scientific calculator. You can also just do it in a Google search. All right, it's 2.5 to the 6th power. You can use the little symbol that looks like a caret. I think it's shift 6. All right, you can also, yeah, the shift 6. You can also just type into Google, what is 2.5 to the 6th power as a sentence, okay? And it's 244. Okay, 244. We'll round it to 240, okay? So what does that mean? That means that to an observer on Earth, Venus at its brightest is 240 times brighter than Polaris is, okay? So your observation of those two objects, Venus is actually 240 times brighter. There's 240 times more energy per second reaching your eye, okay? Reaching your eye. Again, it's observation dependent, okay? So as an actual object, if you get really close to Venus, it's just a dim planet reflecting light of the sun. You get really close to Polaris, oh my God, it burns you up, right? So obviously we're not talking about a feature of the planet or the sun or the star. And I've said it before, but it's worth repeating. All right, but again, what have we done then? Well, we've just understood what this weird scale with negatives means. It's just a way to have a logarithmic relationship between them. And you might be like, well, where's the log? Didn't he mention logs? Well, it's because an exponent is just the inverse of a log. So the fact that the version of the formula that I presented is written like this is because it's easier in some sense to solve for the ratio of brightness using the exponent, than say solving for the magnitude using the brightness, in which case you would have to take log 2.5 of both sides, okay? All right, but what about luminosity? Right? How does this compare to the actual luminosity of the star? Okay? So, luminosity is energy, okay, per second emitted by an object. Okay? It is independent of the observer. So if I was to look at the luminosity of a star, it'd be huge, okay? And that way we could compare the luminosity of our sun to other stars. It'd be huge because it's a lot of energy per second, right? The luminosity of planets is relatively low. The luminosity of something like a comet is tiny, right? It's just a little bit of reflected light. Does that make sense? Okay? So luminosity actually tells us something about the star in a way that apparent magnitude doesn't, okay? And remember, brightness is just a way to interpret apparent magnitude, all right? So now we got the three terms: apparent magnitude, the scale; brightness, the meaning of the scale; luminosity, the actual energy per time emitted by a star. And I say star because that's what we're going to be talking about. We're going to stop comparing to planets. Consider the comparison to Venus a throwback to previous material. Let's move on to stars, all right? So, in doing so, let's mention a little bit of history here. All right. So, a big thing when we talk about features of stars, like luminosity, is going to be the elements that exist in that star. And the way we talk about elements inside a star is something called a spectral, or something called spectral analysis, or the spectrum of that star. Okay, spectrum. I'll show you pictures of a spectrum in just a moment. And a spectrum is light, it's like a rainbow, and it just tells us the fingerprint of particular elements. Because think the fundamental elements, and these are the same elements you'd see in a periodic table, all have light fingerprints, because the spectrum is the type of light that that particular element emits or absorbs. Okay? And so if I was to look at the spectrum of hydrogen, I would see bands of particular colors. The spectrum of helium, bands of particular colors. The spectrum of oxygen, hydrogen, carbon, lithium, so on, right? Any element on the periodic table, bands of particular color, tell me what that element is, okay? And that was a huge discovery, that we could do that, that we could say, look at the light from the sun, shine it through a special device like a prism, observe the colors in that light and say, oh, there's hydrogen in that object, or there's hydrogen in that star, or there's helium in that star, or there's carbon in that star, or there's iron in that star. Interesting, right? Okay, so it started in the mid-1800s, the mid-19th century, with William Huggins and Margaret Huggins. Okay, together they worked on this breakthrough of identifying the lines of a spectrum, okay, other than the sun. Okay, they took the first spectrogram. It's a picture of that light fingerprint of a particular element. All right? So, when they did that, they realized that stars then could get grouped, and other scientists, which I'll mention just one of them in just a minute, realized that stars then could get grouped between those different elements. Because now, just imagine here, right? Now we have a tool, this photograph of a stellar spectrum, and that, just understand that, then can allow us to determine that some stars have molecules, such as iron oxide, some have neutral metals, so elements that would be considered metals, like aluminum or something. Some have ionized metals, because ionized elements can have different spectrums, okay? Then we can look at hydrogen, so some stars have hydrogen, some stars have helium, both neutral and ionized. And if you're not familiar with the term ionized, it just means that some of the electrons are gone, because atoms have nuclei and they have electrons, and if some of the electrons are gone, that's considered ionized. Okay? So that led the way to this idea of spectral classes, because in this figure we have on our horizontal axis, we have these letters that denote spectral classes, and on the vertical axis we have the relative strengths of absorption lines. Absorption lines are spectrum lines, all right? So that we can see then that there's these peaks that correspond to a particular type of behavior for a particular type of star. And furthermore, every one of these letters, O, B, A, F, G, K, and M, not in order or anything, but every one of these letters, corresponds to particular temperatures, surface temperatures of that star. So stars that are in class A, that we know from their spectrum contain ionized helium, have temperatures that are over 30,000 degrees Kelvin. All right? Those are the hottest stars, actually. Okay? All right, so that's interesting. Spectral class O, hottest stars, ionized helium. See, right, that's all information that you'd want to have grouped together. Okay? And then look, if we then go on, we have spectral type B, temperatures from 10 to 30,000 Kelvin, and all those types of stars contain neutral helium, not the ionized. Okay, well, yeah, because ionized means more energetic, so that kind of makes sense that the slightly cooler stars should have neutral helium. Then we go on to the next temperature range, 7,500 to 10,000 Kelvin. Those stars have hydrogen. Then on to 6 to 75, right? And those ones are type F. They're kind of between the ionized metals and hydrogen. Then type G, kind of going quickly through these last ones, 5,200 to 6,000, all right? Then finally, type K, 3,700 to 5,200 and so on, okay? So these are all the common types. There are rarer types, so these are the big 7. O, B, A, F, G, K, M. O on one end, the very hottest stars. M on the other end, the coolest stars, okay? That's a cool star. Any cooler than that, and the star isn't a star. It never forms, okay? So those are the classifications, and we'll talk a bit about their history again in a moment. But let's then take a look at the actual pictures, right? Because on this axis was the absorption lines. I mentioned that's the fingerprint of particular elements. Well, then what does that look like, right? Well, here we have examples from M up through O. You can see within a given spectral type, there's subcategories. So you can have like an MO or an M0 or an M5. You can have an O6.5, right? But remember, O is still the brightest, and M is still, well, I should say O is the hottest, and M is the coolest. So they're still in the same order, okay? And these are the actual absorption lines. So if you look, if you look at type O, you can see that there's these little gaps, okay? Little gaps. Well, those little gaps, there's quite a few of them over here in blue, all right? And first of all, there's actually more. So in addition to there being gaps, which tells us about particular elements, which tells us about particular processes based on physical models that are going on inside that star, there's also just more blue light. As we move down to type M, first of all, there's different gaps. Some of them are bigger, right? Certainly, you know, these gaps are new. These ones over here, right? And this one's fairly new for type M, right? You don't see that gap really at all for, like, say, type B, and that's this gap right here. Okay, so in addition to the gaps changing, and that's, again, talking about particular elements that are absorbing that light, thus it never makes it to us, there's just more red light for M stars, and there's more blue light for O stars on either end of the types. Okay, so that's a big kind of idea that you want to be getting at here, that the hottest stars, the type O stars, that have particular absorption lines and a particular spectrum, okay, that's what this band right here would be, a spectrum, are bluer. O are blue and hot. M are cooler and redder. See the trend? That's a big idea that you want to be understanding. Okay? Lots of different types of stars. We saw it. You look at the pictures, the Hubble telescope, there's all these different colors. We're starting to explain why now. Okay? We took a little foray into understanding apparent magnitude, brightness, and luminosity, but now we're getting into the main content of this chapter. Okay? All right, so here's Annie Jump Cannon. She is famous for coming up with that classification in the 1900s, okay? Well, I believe it was actually around 1920, never mind, okay? All right, but that was her lifespan, okay? Additionally, we have classifications of stars that never made it to being stars. The example that you really need to know is the idea of a brown dwarf, okay? So we look at something like the sun, okay? And then we look at smaller, redder, cooler stars like this one, okay? So notice the sun is a type G star. It has a surface temperature of 5,800 Kelvin. All right, humor me, and we'll go back and take a look. Okay, if it has 5,800, it's in this class, right, class G. So that's going to correspond to a mix of ionized metals and neutral metals, okay? That's going to be key characteristics that we see coming out of a star like our sun. Okay, so but M1 is still a star, right? For that matter, so is M8. But then we get down to T. Well, what is T? Well, T has a much cooler temperature of only 950 Kelvin. Still incredibly hot, okay? But that's surface temperature. The cores are always much hotter of any of these objects. But it's actually that surface temperature is telltale of an object that never became a star, okay? And it's left as a brown dwarf. It's essentially an object that failed to become a star, right? It's massive, okay? Its size isn't much bigger than Jupiter, but its mass is much, much bigger because it did significantly transform. So Jupiter actually isn't close to becoming a brown dwarf. It's a big gas planet, but it would have to have a mass that's over 100 times greater. Okay, and in the process that formed Jupiter, it was never close to gaining 100 times as much mass as it currently has. So it was never close to becoming a brown dwarf. But elsewhere in the galaxy, inside the areas where stars are being formed in nebula, there are plenty of examples of brown dwarfs, all right, that often are orbiting true stars or orbiting each other, right, or sometimes have their own mini solar systems, for all we know. Okay, we haven't analyzed that many of them, but they exist out there as a common object in the galaxy. okay? A failed star, a star that never underwent fusion, a topic that we'll talk about in some detail later on. Fusion is the energy source of stars, okay? Okay, so looking more into spectral lines, all right, we can see differences in the spectral lines from stars of the same temperature but different pressures, okay? So we have a white dwarf that has a particular temperature, but is a very, very different type of object. A white dwarf, totally different from a brown dwarf, much smaller, by the way, is a dead star. It's the leftover core of a dead star. It will be the fate of our own sun in a few billion years, okay? But there are a lot of white dwarfs, stars like our sun that have died before and left behind white dwarfs, all right? But it turns out that white dwarfs are very hot, since they are indeed the leftover core of a dead star. And they're the same temperature as some of the hottest big giant blue stars out there, okay? Which ones are those? The class O stars, okay? But even though the colors are the same because the temperatures are the same, okay? Because that's the thing, the temperature is tied to the color is tied to the temperature. But you know what's not? The spectrums, those absorption lines, those things discovered by the Higgs and the Huggins in the mid 1800s, all right? They're very distinct because the composition, the interior composition, the elements that exist within a dead core of a star known as a white dwarf and a living star called a blue giant are totally different, okay? And so you can clearly see in this picture that there are different absorption lines because different elements exist in the white dwarf and the blue giant. You're not required to know what they are exactly, but that idea that they're different, okay? Another way that spectral lines can reveal information that would otherwise be hidden, because again, the white dwarf and the blue giant have the same color. We might otherwise not know them apart, okay? But we do because of their spectral lines. But another thing that spectral lines tell us is actual motion, because there's something called the Doppler shift. And the Doppler shift tells us that if light is moving towards us, then it's shifted in the blue direction, because blue is shorter wavelength. And if light is moving away from us, it's shifted in the red direction because red light is longer wavelength, because light is, after all, wave. The same exact principle applies to sound. It's when something's moving towards you, it has a higher pitch. When something is moving away from you, it has a lower pitch, okay? Okay, because pitch and frequency, wavelength, all those ideas are related. But what you need to know is if an object, like a light object, a star, is moving towards you, it's blue shifted. If it's moving away from you, it's red shifted. And that type of spectral shift is called the Doppler shift because of the wave nature of light. Okay, so look at the example, right? So red shifted light, it's moved in this direction, all right? So whereas stationary, we see that particular bands, like this black band, okay, kind of drew over it, excuse me, but this black band here is not shifted, right? So here, shifted to the right, the red shifted, we can clearly see it's moved in the red direction. On the other hand, the blue shift is in the blue direction, so it's to the left. So then there's actually a quite big difference between the blue shift and the red shifted, and they both have a smaller difference relative to stationary, not moving at all, okay? So in that way, we can tell if stars are moving away from us or towards us. We can also, when we talk about galaxies, it's a very important principle for understanding if galaxies are moving away from us or towards us, to understand the overall structure of the universe, okay? And additionally, it can tell us about if a star is spinning, okay? So here's an example of proper motion, a star actually moving through the sky. Bernard's star is the famous one here, because it actually has moved quite a bit since 1985 to 2005, right? That's because it's just where it is in our spiral arm of the galaxy, and where we are, we're actually moving relative to each other at pretty great speeds, and so its movement over many years is quite noticeable. There's not many stars like that. Most stars remain fairly fixed over just a span of a couple decades, right? And really, by most, I mean like 99%, 99.9%. So Bird's star is a special example of that. So that's proper motion. You actually wouldn't need the Doppler effect for that, or the idea of the Doppler shift of light, of the wavelength of light. But a lot of times we don't have that, so we can instead look at the movement of objects. These are more proper motion. But we can look at the movement of objects understanding their Doppler shift, okay? And here's the idea that we can look at it in terms of rotation. So if I look at a star that's spinning very fast, its spectrum gets stretched out because sometimes things are shifted in the blue direction, sometimes they're shifted in the red direction because half the star is always moving towards me, the other half of the star is always moving away from me. That means the overall light that's coming from that spinning star, right? A tiny point in the sky. But overall, if we analyze that light, it gets spread out, right? Notice how the yellow band is bigger in this case. See how the whole wavelength gets stretched? Whereas if the star is stationary, not rotating, all the bands of light are much more closely packed together. All the locations of the yellow light and the green light and the blue light and the red light are kind of tight, but when the star is spinning very fast, they get stretched. So that way you can actually look at stars and determine their rotational velocity, which is incredible because it can tell us information about their magnetic fields and how they formed, and exotic stars like pulsars, how they're spinning at an appreciable fraction of the speed of light, and all these amazing factors about stars by looking at their spectral line Doppler shift. And in this case, the stretching of it because of the rotation. Okay? But again, we can also just use it to understand things like motion, right? Just motion of stars, their velocity relative to us. Okay? Here's the idea of rotating stars. All right? So, famous observations of stars and stars' motion we can attribute to Henry Draper and James Lick. There's a famous observatory named after James Lick. All right? And we also bring them up in this chapter because of their relevance to and their connection between astronomy and philanthropy. The idea that there's been a lot of money going into astronomy historically from people that had a lot of money to burn, very wealthy business owners, like today's, owner of Amazon or something, Okay, and I'll wrap the lecture up there. Big ideas, spectral lines, star classification, the letters, the temperatures they correspond to, and the initial material we talked about, apparent magnitude, brightness, and luminosity. What's the difference between the three? Okay, so ask me if you have any questions regarding the topics in this lecture. Hopefully this has really helped kind of focus in on the main ideas of the chapter. And again, this represents a big turning point where we're getting into the main material of the course, stars and galaxies. Okay, the first 3 chapters were just the preamble. All right, thank you so much for watching this lecture video, and I'll talk to you all soon.